Okay, let's continue. So last time we have talked about something about the infinite potential realm, and actually we have the wave function and the corresponding probability density function like this. And here it also mentioned about the normalization. And as you know, this is the probability density function. So when you sum up all the probability density from negative infinity to infinity, it should be 1 because it is the total probability. Just say you roll a dice, can be 1, 2, 3, 4, 5, 6. So all the probability are 1/6 if the dice is fair. And of course, if you have 6, 1/6 add together, then it should be 1. It should be 1. The idea is like this. And some sort of wave function, it can be normalized, which means that if you try to integrate the absolute square of the wave function from negative infinity to infinity, it can be a finite number. Then if you just divide the wave function by this square root value, then you will make this integration to be 1. But for some of the wave function, it is not normalizable. Just say the free particle, the plane wave. When in chapter 39, you know the plane wave, the wave function is something like exponential to ikx, if you still remember. Yeah, and when you take absolute value and square, it is 1, if you still remember, because this is cosine kx plus I sine kx. So if you take absolute value, it is cosine square plus sine square, and then square root, and then you take the square, it's still 1. So actually this is 1. So if you just integrate it from negative infinity to infinity, it is not integratable, because you just integrate something like 1 all the time. This is 1 all the time. And of course, in signal and system, when you integrate this, it becomes a delta function. But here we don't necessarily use it. We will separate some sort of wave function to be normalizable, which means that when we do this integration, it is a finite number. Then we just divide by this square root value of this integration, and then it is normalized to be 1. And some sort of wave function is non-normalizable. But for this case, we can really normalize it, because if we consider A to be the normalized factor, and then so this is the probability density function, and then we try to integrate it. This term will become 1 minus cosine 2n pi over L x, something like this, all over 2. So this term, when you integrate from 0 to L, then it becomes 0. And then this term, half of x, and then evaluate from 0 to L. So it becomes a square L over 2 equals 1. So finally, we have A equals 2 over L, square root of this term. If you still don't know why we can just multiply the wave function by a factor, then probably you don't really know the idea of linearity, because as the Schrödinger equation is linear, so when phi is a solution to the Schrödinger equation in some situation, then if we just multiply by an arbitrary factor to it, then all the products are still the solution to the Schrödinger equation. So we add this normalization condition to make it unique. Only one can be, not more than one can be normalized to one. Okay, so just now I already mentioned something about the 0-point energy, which means for the solution to the infinite square well, the solution starts from n equals 1. There is no n equals 0. Because if n equals 0, then you can simply imagine. If n equals 0, then the phi is 0 at this part, phi is 0 at this part, phi is also 0 at this part. Then the phi is all the way 0, which means the particle doesn't exist. So we cannot have n equals 0. N cannot be 0. Which means that for the lowest energy state, it will be E1, which although it is a very, very small number, but it is the smallest possible energy for the particle inside the infinite square well. And this is called the 0-point energy, which means even though it is in absolute 0 degree, then the particle still have some energy, it's still moving. Okay, so if phi is all the way 0, then it means the electron is vanished, or the quantum is vanished. So we have so-called this 0-point energy. And here is a sample problem. So it says the ground state electron is trapped in the one-dimensional infinite potential well. The width is 100 picometer. So what is the probability that the electron can be detected in the left 1/3 of the well? So it asks if the electron is trapped, the probability being here, So this is 1/3 L over us. Why? Like this. Okay, so what is the probability for the electron to be there? So actually we have the wave function phi x to be square root of 2 over L. This is the normalized factor, and sine of n pi over Lx. And then here we have n equals 1. Which means this is phi n, so phi 1 for the ground state, it should be square root of 2 over L, and then sine of pi x over L. So when we need to find the probability of this electron being here, the probability P1 will be something like phi 1 x, take the absolute value square and then 0 to L over 3 and then dx. So it will be like 2 over L and then integration from 0 to L over 3 and then sine square pi x over L dx. Okay, so so this is just a simple integration, so I just move on quickly. So this is 2 over L, 0 to L over 3, and then 1 minus cosine of 2 pi x over L, all over 2 dx. So this is the half angle formula. Okay, so this one is 2 over L and then 1/2 times L over 3 for the first term, because if you integrate this one, it is x over 2, and then irradiate from 0 to L over 3. So it is this one. And then we have a minus L over 4 pi, and then sine of 2 pi over 3. Okay, so I think you can do it quickly. And then finally, you just need to plug in the value. I think all the values are already there. L and L can be cancelled. So we have all the values. So you can just press the calculator. The probability is 0.196, around 1/5, almost 1/5. Okay, so it also asks you what is the probability that the electron can be detected in the middle 1/3, which means from L over 3 to 2L over 3. Somewhere here. Actually, you can repeat the integration again, and maybe you can just skip to here, and then you only change this to change the lower bound to be L over 3 and the upper bound to be 2L over 3. Then yeah, you can actually do it like this. But actually, this well is symmetric, which means that P1 here is actually equals to P3 here. And then so you can just calculate this this probability to be PM equals 1 minus 2 times 0.196, because P1 is 0.196, P3 is also 0.196. So 1 minus these two values will be the probability in the middle part. So this one is a 0.608. So almost 3/5 probability to be in the middle part. So the next part is about the finite potential well, which means the difference here is that the potential on the left side and on the right side are finite. This U0 is a finite value, although it may be very large. It may be very, very large. And it makes the calculation much more complicated. So that's why we need the infinite square well. The infinite square well, although you cannot provide infinite energy there, but it makes the calculation much more simple. So we will need to introduce that part. But here, this is a more practical case because this U0 is finite, which means if we refer to a finite electric potential, which is possible to be implemented for the something like the quantum computing, 量子计算. So here it says to find the wave function describing the quantum state in the infinite well, we need to consider Schrödinger's equation, blah blah blah. And here we have this condition. So here, as we have a finite potential on the left side and right side, the probability there will not be 0, which means that the wave function for the left part and the right part will not be 0 either. So the textbook doesn't tell you why it's like that. It only tells you that if we have U0 to be 450 eV and the width L to be 100 picometer, then some interesting phenomenon will happen. Then you can see here, this is 450 eV. This is 450 eV, which means the potential, just like this one. So we have a well, we have a finite well, and then the height here is 450 eV. Okay, so under 450 eV, we have quantization. We have E1, E2, E3, E4. They are quantized. There are no continuous energy inside this well, which means if the particle doesn't have enough energy, which means it is still trapped in the well. It's still trapped in the well, and its energy is quantized. It has E1, E2, E3, E4 in this case. Of course, following this number, if you change the number, the value will be different. And if the electron have more energy, then it will not trap by this well anymore, and the energy there is not quantized. It is continuous because it is free. It is free. You can change to any of the energy because it is already free. So you may ask how can we come up with this number? It will be extremely difficult. It will be extremely difficult. I have tried to solve it last year like this. So actually we need to write down the Schrödinger's equation, and then of course, first of all, we assume that the E is smaller than the U0 to find the quantization part. And then we try to solve for X is smaller than 0, which means the left part of the well here. And then in the middle, it is like this. In the right part, it is like this. So in the middle part, it is still a standing wave. It is something like B cosine kx plus C sine kx. Yeah, somehow similar to the infinite square well, but for the left part and right part, we still have this second order ODE, but the coefficient is negative. So it will become a exponential function, a real exponential function. And for the left part, we ignore the negative coefficient, negative exponential part, because it should be something like it should be something like this. And for the right part, it should be something like this. It should be something like this, not the other way around. So in this case, we will ignore the negative exponential like that and like that. We don't like that one, because it will go to infinity for infinitely far away, which does not make sense because it will make the probability to be infinitely large. So in this case, the wave function for the left part and right part will be exponentially decay. So this is very interesting because you can see this is a potential well. This is like a wall which is not high enough, which is not infinitely high. And actually the quantum, the electron here, still have some probability to enter the wall. But if it try to go deeper, then the probability will be attenuate very fast. So actually it still has some probability to go inside the wall. But it mainly will be trapped in the well with a standing wave, in a standing wave. So this is only the first step. You can write for the region 1, we have something like this. Region 2, we have something like this. We have region 3, we have something like this. Then we will need to use the boundary condition to solve for A, B, C, D. And then this is continuous. And then the first derivative is continuous. And then at L, wave function is continuous. The first derivative is continuous. So we can write 1, 2, 3, 4. I just go through it quickly. And then we need to solve for K, and then try to find the relationship between A, B, C, D. So if we just plug in A 1 to 2, and then we can find the B and C has this condition. And then plug in 3 to 4, we have something like this. Oh, it looks so awful. Okay, so So this is 5, this is 6, and we will plug in, if we just divide 5 by 6, then B, C will be cancelled. We only have a K and L in this equation. So, and then we do some trigonometry calculation. We can find that tangent KL equal to this one. And then we further need some calculation. You can find that D equals plus or minus B, and that, but I don't try to go in deep. And then finally, we can find a equation like this. Tangent square root of 2MEL over H bar equals to this one. So in this case, you can see 2 is a constant, M is a constant if it is a fixed particle. E is the variable we need to solve because we try to find the energy level. And then H bar is a constant. L is a known value because we know the width of the well. So E is the unknown value. And on the right side, U0 is also known value because we know how tall the wall is, how tall the well is. So on the right side, we also have E on the right side. And actually, we need to solve E for this equation. But actually, this is a non-linear equation, which is not possible to find the analytic solution. For some of the non-linear equation, you can find the solution. Something like if you have, for example, if you have a sine x equals 1/6, you can find x to be something so n pi plus arcsine of 1/6, something like that. But here you cannot solve for this. For example, if you have a sine x equals x, I suppose this one is not solvable. You can only use the numerical method to find the solution. And this is actually the same case because you can see you cannot take arctangent, because if you take arctangent, you still have E on the right side. Then you cannot find the solution. You cannot rewrite E equals to blah 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 blah, something like that. So actually, we need to use some numerical method to find, and then of course we can of course use a computer program to find the value. But actually, I just try to verify the value given by the textbook. Try to plug in this value and then try to find, or you can use some iteration method to find the solution. And finally, you can find that actually this energy level is actually the solution to this equation. So I just mentioned for the finite potential well, it is more practical, but the calculation is very tedious. And then maybe for some of the method, you can something like you have an initial value, you plug in the left side, and then you try to solve for the right side, and then you plug in the value to the right side and then try to solve for the right side, and then you do some iteration. Sometimes it will converge to the solution, and this is probably the case. So finally, we can find that we have some. This is the energy level. We have the energy level like this, and then of course, when we try to plug in this energy level back to this equation, you can find the wave number of the corresponding wave function, which is something like this. And then when you know the wave number, you can also find the wavelength of the wave function, which is something like 62 picometer, 80.5 picometer, 119, 236 picometer. And if you still remember, the width of the well is 100 picometer. So this is not actually a half of the width or something like that. They are not actually multiple to the fundamental, because the well is finite. So it makes things strange. So this is approximately 4 times, but not actually the same. Yeah, something like that. If you multiply this one by 9 is 240 something. So yeah, it is still similar to the infinite square well, but not actually the same. If you really need to find the precise value, you need to solve for the Schrödinger's equation. So finally, we can find this is the probability density function. If you really want to draw the wave function itself, for the fundamental, it is more or less the same, and you can see here, this is continuous. The value is continuous. Also, the slope is continuous, which means the first derivative is continuous at the boundary. And for the second wave function, which means the first excited state, this one and this one looks a little bit different. Because this one we already take the absolute value square, so it is all the way positive. Because for the probability density function, it must be between it must be a positive value. It doesn't necessarily to be between 0 and 1. It must be positive value at this. But for the wave function itself, this is something called an anti-symmetric, which means for this point it is negative value. It is something like this. It goes to the negative part and then go back here, and then go to 0 for infinitely far away. And for the third one, it is still symmetric. It is still symmetric, which means that this point and this point have the same height, something like that. And if you take the absolute value and then square, it becomes this way. This is why when we try to solve up to here, we have d equals to plus or minus b. For d equals to b, it is a symmetric case. For d equals to negative b is the anti-symmetric case. If you have interest, you can contact me to get derivation of this, but I don't think it's very important. Yeah. Just let you know. Yeah, almost every equation or every numbers can be derivable. Okay. Okay. Maybe let me finish off this sample problem. Okay. So this is easy. So suppose a finite well U0 blah blah blah, which is actually the same case as before. So what wavelength of the light is needed to barely free it with a single photon? Absorption. Which means yeah, actually it says the electron is in its ground stage, which means it is as E1 here. It is at E1 here. Maybe I just open this one. You can see. No. Okay. So it is at its ground state, which means that if it needs to escape from the well, you need to provide the energy from E1 to up to here, then it can escape. So here, the energy will be U0 minus E1, and then U0 is nothing but 450, and then E1 is 27. So you need to provide 423 eV so that the electron can escape the well. It can be free. So actually, we need to find the wavelength of the incident wave. So lambda will be lambda will be hc over u0 minus e1. Because if you still remember, we have actually the delta E to be HF, and if you still remember, C equals F lambda, C equals F lambda. So here we only have a lambda, we don't have a F, so we should have a F equals C over lambda. Yeah, like this. So we have HC over lambda. So if we move this lambda to the left side, delta E to the right side, it is actually this one. So we only need to plug in the values, 6.63 times 10 to minus 34, and then times 2.998 times 10 to the 8th power, all over 423 times 1.6 times 10 to minus 19. Okay, so so this is 2.94 nanometer, which is quite a short wavelength. As I mentioned, the visible light has a wavelength around hundreds of nanometer. So this is much shorter than that, which means energy of the wave has a much higher energy. So for part B, can the ground state electron absorb light with lambda equals 2 nanometer? If so, what then is the energy, electron energy? The answer is yes, because if it absorb the energy with 2.98 nanometer, it barely goes to here, which means that it spent all the energy to get rid of the potential. So if it absorbs a shorter wavelength, then it can go higher, because the energy band here is continuous. You can always find some energy there exists. So actually, HF equals HC over lambda, which is 6.63 times 10 to minus 34, and then times 2.998 times 10 to the 8th power, and then all over 2 times 10 to minus 9. So this value is 9.95 times 10 to minus 17 joule, or in eV it is 622 eV. So this is the energy it gets. So the kinetic energy will be this HF minus this U0 minus E1. This U0 minus E1 is the energy it required to escape from the well. And so this energy is for escaping. So the remaining energy will be the kinetic energy of the electron. So it is actually 622 minus 423. 423 is actually here. So the answer is 199 eV. Okay. So this is some simple calculation. But actually, I think this is very interesting here. Okay. So I think I finished off all the physics content in this semester.